Hello, I am Brett Willman from the International Space Station program. I'm the Deputy Manager of Computer Resources for the space station. I'm also the ISS DTN Implementation Project Manager. I have two colleagues here, Suzanne Davidson, she's one of the lead Boeing DTN architects, and Tyler Dubrava, who has built and designed and coded a piece of software that ISS uses 24 hours a day, and then we're looking at putting DTN on. So they're here to answer some technical questions in case I can't answer them all. So I'm going to start high level and then kind of delve down into what ISS is doing with DTN and then open it up for questions. So let's go to the next slide. So ISS is a massive engineering feat, orbiting the Earth at 90 minutes at 17,000 miles per hour. It's gigantic. There's 6 crewed members at all times on ISS. The area inside is roughly the size of a 747 Boeing jumbo jet. It took a lot of time to build, 187 spacewalks, and 205 different people from 15 different countries have been there. To put it in terms that maybe some people here in DC might be able to relate to, the solar array itself could fit in the Senate chamber 3 times over. So the vision of ISS is a world-renowned laboratory in space, enabling discoveries in science and technology that benefit life on Earth and exploration of the universe. Next slide. And its mission is to advance science and technology research, expand human knowledge, inspire and educate the next generation, foster the commercial development of space, and demonstrate capabilities to enable future exploration missions beyond low Earth orbit. Next slide. So on ISS, we've performed over 1,500 mission experiments with more than 1,500 scientists across the world. And they've encompassed all sorts of fields of research, including environmental control and life support systems, human research, materials research, and I think something that maybe not everybody recognizes, but the International Space Station covers 95% of the population of Earth. So in doing so, we have a good view of Earth and are able to do payloads that look at Earth on a continual basis. We also are heavily working with students across the world. We've reached out to over 30 million different students to participate in experiments on ISS as well as communicate with the crew to do live interactive sessions with. Next slide. So in exploring space, we're using ISS as a platform to go further. We're using it to do exploration technology demonstrations. We're trying to validate technologies on ISS so that we can use them in the future vehicles that will go further beyond the Earth orbit. We're trying to mature critical systems that will be needed in those vehicles so that they're more reliable, more efficient, lower power, and lower mass. We are doing a lot of research into health management and for what it means to be in space for a long duration time. As you may or may not know, Mr. Kelly and Mr. Kornienko is on ISS right now. They arrived in March, and they're there for the first year-long duration space flight on the International Space Station. And we'll be looking at them to do the research necessary to determine what it does to the human body at a molecular level, at a muscle level, bone level, ocular level, for being in space that long. And Scott Kelly is unique in that he has a twin brother on the ground, so they're able to mirror each other and look at each other's development, one on the ground and one on orbit, which is really neat. And we're also using ISS for op scenarios. We want to know the operational techniques of how to plan and execute missions that go further into space with the crew. And so we're trying to, on ISS, solve some of those issues. Next slide. So from the previous slide, you saw maturing critical systems as being one of the goals for future exploration. And you'll see that we're working on a lot of different projects on ISS to do that. We're looking at a new docking system on ISS that can be used for other spacecrafts. We're looking at the next generation EVA suit that will be demonstrated on ISS. We're doing some air quality, radiation monitoring. All of those will be critical for future flights. And one of the goals is also disruption and delay tolerant networking. and we're implementing that on ISS right now. And the idea here is DTN will be the comm standard for future spacecraft at some point. All right, so what exactly is ISS doing? So ISS is implementing DTN as nodes on the space station. We're also implementing the architecture on the ground. And the whole end game here is to allow payloads to be able to operate using DTN and to be able to do their science by uplinking and downlinking data, command and telemetry using DTN, and that allows them to minimize the amount of people that they have at their control centers. And so what they can do is they can say, start payload, do your data, downlink it, and the payload developer is irrespective of LOSs, AOSs, the lower level protocols that are below that. And all they really need to do is tap into the APIs of DTN to do their science. And we're providing the packages for them to do that. Another key component for us of this is that it's COTS software. It's software that you can find on SourceForge, as Vin said. It's software that's out there, and that was very helpful for us to get the stakeholders' interest to sell this off. And of course, we're wanting to use ISS to gain the knowledge necessary and experience to use it in future spacecrafts. Next slide. So DTN on ISS is not foreign. We've done some developmental projects on ISS already. One of the first projects to go on board was the Commercial Grade Bioprocessing Apparatus, CGBA. And I'd like to say I apologize if there are a lot of acronyms in here. NASA's known for a lot of acronyms. I've tried to spell them out and be happy to answer questions at the end if there's one that I may have missed. But CGBA is one of the first ones to use DTN on ISS. It was an asynchronous system. It used the S-band architecture, which is a low-rate uplink system for the uplink of bundles, and for the downlink, it uses the KU-band system, which is the high-speed link to ISS. We also did an experiment with spheres. Spheres is a synchronized position, hold, engage, and reorient experiment satellite.
This is the Star Wars stuff.
Yes, this is the Star Wars stuff. Yes, spheres is this little ball that has nitrogen canisters on it and moves around, reorients, has a camera on it. It's just like what Luke Skywalker did on the Millennium Falcon as he was with his lightsaber, yeah. And so Spheres used this on their smartphone to downlink video for one of their experiments, and it was very successful. ESA has had an OPSCOM project that they used DTN for, and it was a laptop doing software downlinks. And we have future planning for DTN services. Right now, ESA is going to be doing their OPSCOM 2 payload. This project is going on in September. It's not going to be integrated into the institutional architecture that I'm putting out here, but it's going to have all the capabilities and hooks to be added to it when ours comes in place. And of course, we have a couple others. Telos Science Resource Kit demonstration payload. I have more on the next slide on that. And ESA is investigating putting an ESA node in the Columbus module, which will then connect to our infrastructure and allow their DTN payloads to have their own interfaces so that they don't have to come to NASA to interface to DTN. And of course, we've also been talking to other IPs. JAXA has done a lot of ground DTN testing. They're interested in doing DTN testing on orbit, and so is CSA. Okay, so TREC, the Telescience Resource Kit, this is a phenomenal piece of software that is provided by the Huntsville Operations Support Center, the HOSC. The HOSC is out at Marshall. I might say the word HOSC. You can also kind of think the Payload Control Center, so I might say Payload Control Center as well. The HOSC is developing the TREC software, and the TREC software is a piece of software that any payload developer in the world can go and request and downlink. And what that enables them to do allows them to take this TREC software and put a module on their payload, and that can be Linux or Windows. And that module will have DTN resources so that that payload developer can interface with this TREC software and be integrated into the DTN architecture. And there's also a module on the ground that will go at their control center, the payload control center outside of Marshall, and allow them to have the links on the ground that'll provide the end-to-end architecture for them to do payload science on orbit. So with that, they'll have a a set of capabilities to allow them to transfer files, to configure and manage the DTN nodes. Also in the Trek software, it has all of the hooks and scars that allow them to connect to the HOSC resources. You can't touch your payload on ISS until you've logged into the HOSC, put your right credentials in, and then it sets all of the firewall and security policies to access your payload. So all of that is integrated into this Trek software, and it's really neat. And I encourage anyone that was interested in looking at that, we can set you up with getting you in contact with the right people to get this software. Next slide. So here's a little diagram of what I just described. You're a payload guy or girl at your payload control center. You're using your Trek software. You use the Trek software to log into the POIC, which is the Payload Ops and Integration Control Center. You log into the systems there. It creates the links in the ground system, PDSS and HPEG systems. I don't know all those acronyms. And then that provides you the access to your payload on orbit. And on orbit, you have the the Trek module in your payload, and then you have your end-to-end link to do your science data. And it's meant to be as easy as possible to get your payload on orbit. Next slide. So another piece of software that we're going to be implementing DTN on is called swordfish, and it's a pretty nasty acronym. Software to ready data files to send hastily. I think that's NASA creating an acronym before we actually had the words for it. So this is a NASA designed and developed software to handle flight control team file transfers and computer administration. And actually Tyler here is the one that designed and coded this entire piece of software. It's a custom protocol to handle the ISS delays and disruptions with minimal flight control team interaction, and allows the flight control team to queue data for uplink and downlink in jobs and automate their ops. And the system allows for system-wide deletion of files as it's flowing across the system. So if a flight control team says, oh, I want to stop this, it can stop it in a point. And the architecture of Swordfish is similar to DTN. We actually have an aggregator on the ground, which could be thought of as a DTN node that does aggregation of files before they're sent an uplink. And that DTN node is where you would have bundles. He has something similar to that in the Swordfish. So DTN does seem like a great place to put in here to remove some of these custom protocols. And then it provides other laptop administrative tasks such as reboots, directory file lookups, and stuff like that, which will be bundleized. Next slide. So as we've been running this project, we couldn't have done it without a lot of community coordination. And that starts with Santa. We started with them to get our node IDs officially documented. So we went to Santa. I'd like to thank Lee Pitts for that. He coordinated with the Santa administrator and was able to get us a block range of node IDs that the ISS now has, and we can delegate out to the payload users so that they can have node IDs both on the ground and on orbit. And we've created a plan to allow payload users to come to NASA and request these, and we have a whole process to get that to them easily. A second item that kind of came up with us is STCP versus TCP. Two different ways of doing TCP as your convergence layer. And we went with STCP. We provide both. Both are as an option, but we kind of went with STCP as our default because we saw that it was getting better performance, and particularly in the presence of disconnections with our SSC laptops on orbit. Our SSC laptops are crew interfaced, and you find that the crews will take these and move them around, go from wired to wireless. You get disconnects there, and they reboot. I mean, you're in a space environment. Every once in a while, they just reboot. So we found that it performed better with that, and we were able to work with ION to implement additional flow control mechanisms that were built into the Swordfish software that kind of takes some of what we did in Swordfish and now can be implemented into this convergence layer. And we found that the complexity just overall is simpler with STCP, which is why it's called STCP. And that the TCP convergence layer was just more complex than that. We also worked with the ION community to be more ISS friendly. One of the things is that we can now develop in Visual Studio. That was a good need to us. We implemented the metadata extension block, which allows for file transfer jobs to be linked directly to bundles. As I mentioned earlier, with the Swordfish software, we're able to delete files system-wide. This linkage helps us to do the same thing with DTN. There's some updates to LTP to make it more efficient with when data loss is high. So there's some reporting there that helps us. Next slide. I kind of mentioned this earlier. We added some error handling to STCP to make it more efficient when connecting to laptops. So instead of closing a socket, it'll just send to reconnect, kind of more efficient on resources. And we also improved the TCP convergence layer bundle receiving functionality. We also, at the HOSC facility where they're operating DTN2, had some updates to interact with ISS better. And one of those was to add new convergence layers, LTP, UDP, and STCP. We also, with DTN2, had to update the software to run better on modern systems. We have virtualized environments at the HOSC, so we had to do some updates there. We had to harden the code base a little bit to get the 5 nines of operability, because we'll need to make sure that we get a reliable system for payloads to use. They implemented some additional features to interoperate with ION. Of note here is the aggregate custody signal and the extended class of service. And we included the deletion of bundles that were not delivered due to duplicate suppression. Next slide. Boeing actually developed another piece of software to help with Swordfish and DTN overall management. It is a daemon that is going to run on our node on orbit that allows us to, one, get some statistics from our operating nodes on orbit from a DTN level. In a way, it's a little bit of network monitoring. 2, it allows us to get to those files and bundles that are attached to a job and file ID that we can delete them before they are fully transmitted. And it also allows us to do some remote administration, like updating link rates across the system. Next slide. So the DTN system architecture, the way that we've implemented DTN on ISS is that it is going to be an exclusively KU band service for the first iteration. The main reason we've decided to do that is based on the software that's available and the way that we manage the KU band link. The KU band link is a TDRS accessible asset, and it is CCSDS based, but all of the users that use the bidirectional KU band link are Ethernet IP based. And it just made it the most logical sense to start here. And there also happen to be our highest data rates. We have a high rate uplink and a high rate downlink. And since we are operating over that TDRS link, we decided that it would make sense to use LTP for our space to ground comm link. And we are using LTP for that. As part of our architecture, we do have hardware and support at the HOSC, the Payload Control Center, and the Marshall. And we also have support at Mission Control Center. Again, the HOSC side is the payload side. Mission Control Center is your flight control team and interfaces to crewed assets. And the HOSC and Mission Control Center are responsible for arbitrating the users on the ground to getting access on orbit. So there are systems in place to make sure that the right people are accessing the right resources on orbit. All right, next slide. So this is a diagram, a high-level diagram of what we're implementing on orbit. And we have it color-coded as blue for operations side, your MCC flight control team side, and green for your payload side. But really, they're all interoperable. Your green payloads could use the blue assets, blue DTN nodes to go down the blue side, and vice versa. You get blue down to green. But this is a good way of kind of showing the segregation between where we're trying to subdivide our assets. On orbit, we have 2 gateway nodes. There are going to be 2 laptops on board running virtual machine software. The VMs that we've created one for a payload DTN node, and we've created one for the ops DTN node, and we have 2 laptops. So both of these VMs are on both of these laptops, but we're only going to have one operating at a time. So That's why you see two boxes on each side. We'll have one running as prime for ops side, and we'll have one running for prime as the payload side. And if we have a laptop failure, which we do, laptops do have, once or twice a week, you either have to do a reboot or you get a single event upset. You could fail over to the other one, start up the VM, and you can then run it down that VM. And then on the ground, the channels for the KU band system, we have a channel that goes to the Haas, we have a channel that goes to the MCC Houston, and we have nodes on the ground there. On orbit, we're running Ion. On the ground at the Marshall, we're running DTN2, so it is a heterogeneous mix of software we're using. And at MCC Houston, we're also running Ion. And you'll see what's unique here on the Marshall side is that we extend the payload DTN users out to their remote sites so that they have DTN capability out there. And that's, again, through Trek software. All right, next slide. So we've actually started implementing this, and we've developed the architecture, we've developed software, and now we're into testing. We've completed numerous successful engineering and integration tests across the labs. We're using test tools such as BPing, BP Echo, DTN Perf, BP Driver, BP Counter, CFDP Test, and we've been using the Trek software as part of one of our test tools. We have that available at both facilities. And as you always learn with testing is we've got some lessons learned, we've had some updates, we've been working with the teams and flushing these out. We've been tweaking variables and parameters in the system to get as much juice as we can out of it. Next slide. So I don't expect you all to be experts on this diagram, but what I'm trying to convey in this diagram is that we have our software development integration lab in Houston, and in particular our joint station land lab, which is my lab, out in Houston at Johnson Space Center. And that's a very high fidelity of ISS on-orbit architecture. And that JSL lab is connected to assets that are flight-like and simulate the TDRS comm systems. And those are directly connected to the same MCC Houston assets that are flight systems at Houston that go to flight assets. And we do the same thing at Marshall. We have flight assets there that we connect to from our labs. So we have a very high fidelity lab environment that models ISS. And that's how we're doing our testing. And so we have some data, some preliminary data, and we can get into more details and questions if anybody has some questions on it. So next slide. Using LTP configured at 25 megabits per second downlink and 8 megabits per second uplink, we're getting about 80% efficiency in our data rates. We're getting about 20 megabits per second downlink using LTP, 20 megabits per second, and 6 megabits per second uplink. And we have seen some inconsistencies that we're investigating. For example, smaller bundle sizes are having different results in a couple of test runs. We've seen, for whatever reason, 2 megabits to 8 megabits per second for smaller bundles. And we're looking at that. We think we'll be able to fix that. We've changed the settings across all these tests to make sure that we can get the max bandwidth out of this. And we've also had updates to software. We've recoded and recompiled and installed software based on what we've tested to. We've fixed some crashing on the external router at the HOSC. Report segment ACKs not being timely processed. We noticed that happening. We also noticed an inconsistency between the ION node and the DTN2 node on how when the aggregate custody signal handling an ISS node did not have ACS enabled, there was inconsistencies on the DTN2 node, and we were able to fix that. And we also have other test capabilities. So not only if you're a payload developing to use DTN and using some of the packages we're providing or creating your own packages, you can bring your payload out to my lab and leave your ground facilities that you're on and use all these same facilities that I showed you in that diagram to do a full end-to-end test. You can do that. You can also bring your payload to just my lab. We have representative capabilities, ground capabilities that are representative of the real things at our lab. We also have the same thing at the HOSC. The HOSC has a mini ISS in their lab, and you can then have your payload control center that's remote, log into the HOSC systems, and operate a payload that's at the HOSC. So all of these exist in order to make the payload validation and verification simpler. Let's see, next slide. We also have created a box that is ISS in a box. It's called the Remote Advanced Payload Test Rig, Raptor. And what this is meant to be is this is meant to be a box that the payload developer can check out and put on their test stand and have their ground system right here, their flight system right here, plug into the box and have and be able to simulate ISS up to and including DTN. This box also has the capability of being linked into the HOS so that you can even test your remote access capabilities with the HOS system, so that you make sure all of your software is working, not just in your own internal environment, but you can actually log in and then come back to this box. So this is a really neat thing to allow payload developers to not have to come to NASA. All right, next slide. So if you can continue clicking, and got some pretty pictures. So we are expecting final software load deliveries of our on-orbit nodes to be delivered here in June for our final formal testing to be in late June. We're expecting Trek software delivery to be in June to support that. At the end of June, we are going to light up the links across my lab all the way to the Payload Control Center in MCC Houston, have it all live at the same time. And we're going to go through a formal process of checking off all of the steps necessary to verify and validate that this system works. So we're on our way to having the system delivered sometime in July, at which point we will start publishing all of our ops procedures and engineering procedures so that our operators can then have the time necessary to create interface procedures and procedures to deploy this on orbit. The Trek ISS demo is slated for November to be ready for an ISS deployment at the end of the year. So we're hoping to go live by the end of the year and be able to do our first Trek download using DTN. So let's go next slide. So as I've kind of mentioned before, we're using DTN to mature exploration and use this as a platform for future growth into space exploration. We're also looking at the DTN bundle encryption and security. I think that's going to be one of our most important tasks after we get the system and get payloads using it, is to provide some levels of authentication and security to the system. We are also looking at using DTN for some of our commodity infrastructure that isn't necessarily DTNized right now. And I'll use the examples of our inventory management system. That's all IP based right now. COTS, well, actually it's in-house developed, some COTS software. Updating crew procedures to use DTN, and one other item that actually has been a part of a project that was, I forget the name of the project, but was actually given out to the community as a research project, was to implement DTN with Outlook. That's been a big problem for our crew members on orbit, is they'll send an email down and it'll have 10 megs in it, and it goes to a snail's pace because it's using TCP across this connection to downlink. So right now we're evaluating responses to this research proposal, and hopefully we'll be able to use DTN with Outlook here soon. We're continuing to work with our international partners and commercial visiting vehicles to see if DTN is something that they want to pursue. We'll have the architecture available for them to use. And then ISS is also looking at future comm systems, be it KA or laser systems, because we're getting a lot of data from ISS, but we always need more. There will always be payloads taking pictures, and pictures just get larger. So we're looking at DTN as being a potential implementation, because some of these comm systems won't be as continuous as the KU band system that we have on orbit, and DTN will be the trailblazer for doing that store and forwarding for it. Next slide. So I'd like to thank a lot of people for helping me put this slideshow together. Adam Schlesinger is our JSC representative for DTN. He's been very helpful in working with getting ISS implemented DTN, but also extending DTN into the JSC resources. He's also been leading the effort to getting DTN over Outlook. Lee Pitts, probably some of you here know. He's our Marshall lead architect for DTN, and he was extremely helpful in putting some of this information together. Kelvin Nichols and Jeff Lippincott deal with the Trek software. So Jeff Lippincott's been working with Scott Burley on updates to ION to make sure that it works well with the Trek software. David Zollard, Dennis Botts, all people at the Marshall Control Center have been very helpful. Tyler DeBravo, who's here with us, is our Swordfish DTN integrator. Bill Polchek, Larry Weiss, and Jim Wehoff all work at Boeing. Jim helped do a lot of project management with me, and Bill and Larry have actually developed the DTN node on orbit and deliver that software to be loaded onto a laptop, and I've also developed the Swordfish management daemon, so they've been extremely helpful. And I think that's all I had to say. I'd be happy to answer as many questions as possible. And if Suzanne and Tyler could grab a wireless microphone, because some of these are probably going to be questions they might be able to help me answer.
You need to add one more name up there, Scott Burley.
Oh, yeah, well, Scott's here. Scott Burley, of course. He's been helping us with the ION development and been invaluable to us.
It's Vince Cerf again. Let's see, you already answered the question about the KU uplink, so thank you for that. One question about the current occupancy on the ISS, and this fellow who's going to be there for a year. Is there any reason to think that the results we get from this gravity-free environment will be applicable to future missions where we might establish artificial gravity using rotation, like the, 2001 movie? Is that actually feasible, and would it make a big difference? Because it's pretty clear, we know now that lots of bad things happen to our bodies when we're in a gravity-free environment.
So this is a generic question on ISS, whether we can do some type of gravity on ISS. Is it ISS or just in general?
The thing doesn't look like you'd want to be rotating the whole shebang, but maybe you could have a little gerbil race wheel somewhere.
Right. So a part of the original design was to have a centrifuge module. It was called the CAM, and I don't know all the politics of why that didn't get designed. I think it was actually they started development on it and they repurposed all of that to build another module. Yes, there's been discussions on doing some type of microgravity, but at a lower level, providing 1/6 gravity to do some payload research as it would be on a moon or somewhere else. I don't have all the details on that, but I can tell you from a cruise perspective of being able to maintain bone growth and muscle and ocular development, it'd be invaluable if we could have something like that. I don't know where we are in actually implementing something like that.
The astronauts I've talked to basically say when they get down after an extended mission, they're having trouble walking and establishing balance and all the other stuff.
And it takes weeks. I hear stories all the time about a crew member that's come down, will be at home with their wives, be drinking coffee, and then go boop. Yeah, and the coffee's on the ground.
Well, that's a different problem. It's psychological. Yeah, I can just let it go happen. What was that? I have a different question, and it has to do with the deorbiting of ISS. Is the current schedule to shut it down 2020? Am I remembering that right?
2028, I believe.
2028. Okay.
I believe it's
so
2028.
Much more time than I thought.
I'm not 100% on that, but I believe it's 2028. And I believe Russia is looking at extending their certification through 2024. And it may be that some of the international partners are rated through 2020. It's an international effort, so everybody has to be involved.
Yeah. Well, the question is, if it is not occupied, could it still be used in some way as a relay, for example, or could we do experiments? Could we leave things on board that we could?
That's a very good question, because if it's not staying in orbit, well, so one, you got to look at the logistics of that. How do you get the resources to ISS to keep and maintain its orbit? So there's going to be some logistical effort there and cost that you have to weigh. Two, if you're not doing that and you're not keeping it in orbit, which again requires a lot of effort, you're having to take it down. And then that is another logistical effort in how you deorbit something like this and bring it back into the atmosphere safely. Piece parts or whatever. It's going to be a heck of an engineering. It's going to be just as much an engineering effort to take it back than as it was to put it there.
There's a lot of stuff coming down as a result. Okay, that's all my questions.
there any questions online? Oh, we got a question in the back, Suzanne.
Hi, George Minardos from .build Registry in Santa Monica, California. I was wondering if you could tell just a little bit on using DTN for the robot-controlled process from ISS to Earth. Didn't the ISS control a robot via the DTN protocol?
You're right, and maybe Suzanne has a little more details on it. There was a robot that was commanded at Ames using DTN, and I don't have the details on it. I wish I could tell you more about it, but if you give me your information after this, I will see if I can pull together a pitch that kind of talks about the results from that experiment. Yeah, I know what you're talking about. It was about a few years ago that happened.
Wait, there's Metaron, which was controlling a small robot, and now there's a more advanced one, as you know, scheduled, and you mentioned that. But
The
was this
OPSCOM?
more a humaniform robot?
Yeah, I'm not sure if OPSCOM was using DTN, if that was the payload moving robot DTN payload. I think it was a different payload that wasn't necessarily DTN. I know what you're talking about with the ESA one.
Yeah, there is Robonaut, which is
Sure.
a different thing. That's a General Motors NASA collaboration. But
Right.
I didn't know how, I saw it, I didn't think it's ever been put up on the space station, do you?
Robonaut?
Robonaut.
Robonaut is on ISS right now. We've actually
is
attached.
on ISS?
Yes, oh yes, it's been up there for about 2 years now.
Ah,
And it is it actually has legs now. It has a torso and legs now, so it is allowed to monkey across ISS in a very contained environment.
Yeah, Elon keeps worrying about stuff like that.
Robonaut is commanded at the Mission Control Center in Houston by the engineering department. Right now, it is not using DTN.
No, I didn't think it was using DTN at all, but I was just thinking it was yet another interesting thing but I didn't know if it had been put up on the space station. I met it while it was still on the ground.
It's a very neat payload. There's a lot of opportunity there, especially if we can figure out how to make it external to ISS.
Yeah. Some of you may have read a book or heard of a book by, it's the gal at MIT, Sherry Turkle. It was called Alone Together. It was mostly about young people not talking to each other on the phone because they text instead. But her early part was about humaniform robots and our reaction to them. And her point was that if it looked like a person, that we imbued this thing with more social awareness and consciousness than it actually had. And so when it didn't pay attention to you, you felt insulted or angry or something or somehow diminished. So she was worried that we would offer to these things a lot more smarts than they actually had. And so she thought making things look like people was a bad idea.
All right. Oh, got a question?
So will there be a conclusion to the never-ending story of us waiting for the operational communication go live for DTN on ISS?
Are you asking when we're going to go live?
Yes.
Well, okay, so scheduling activities on ISS is tough. It's really tough right now with logistics and space flights, especially with the Progress vehicle that we had issues with. We're eyeing December. So the process is that we put our requirements into the requirements program, and we are on a current requirements document to get operated in increment 46, I believe, and that's the December time frame. Now, it's kind of a chicken and an egg thing. If you don't have a payload, why would I spend the crew time to deploy the system? If I don't have the system, why would a payload go and put the payload out there? So we're fighting that battle right now. The Trek workstation is our best opportunity. It's a demo that's going to go on board and actually demonstrate the link, not just for DTN, but for other purposes. And I think that's our best opportunity to piggyback on that project to be able to get these laptops deployed. Personally, I don't see any reason why we can't deploy this in December. And as I said, it's an evolving thing. If we have flight delays, our hardware's there, the laptops. So if there were flight delays that opened up crew time, that it makes it easier to push this requirement into the actual crew time. So it's it's hard for me to really answer that. That's why you got to put a target date right there.
The other thing is, DTN is being offered as a service now, to our payload agreements. But it's also education. We're still trying to teach them and tell them what are the benefits of DTN, why should they use it, and so it's a continuing game of just educating our payload community and other operations on the benefits of DTN.
That's a very good point. We're developing all these products, but unless the payload developers out there recognize that this is a tool that makes life easier, and like she said, we've developed these products to help educate them, and we just need them now to say, okay, it's there, it's been delivered, and now we need to use it. That's our next major goal, is to get payloads to use it.
So this question is from Scott Johnson. I am unclear why protocols are being tweaked to suit the needs of proprietary MUAs as opposed to the other way around.
So when you say tweaked, we're still using custom protocols. All the protocols are custom. What we've asked for, and most of what is in here, is efficiencies within the actual operations of that software. So for ION, for example, maybe Tyler can talk a little bit about some of the changes he's asked for that don't necessarily change the open source nature of it, but rather actually how it's used. So maybe you can answer that a little better than me.
Well, first of all, to make sure I'm addressing your question properly, can you please repeat it? So the question is, why would we be tweaking these protocols to suit NASA's needs? And in the case of swordfish in particular, we're actually not tweaking the protocol. We are tweaking the implementation. We've worked very extensively in testing with Scott Burley and asked him to change the behavior of ION a little bit to better suit our needs. ION has been designed very well for its original purposes, literally interplanetary missions of very long distances, where you carefully schedule communication opportunities. That is not necessarily the environment that we want in the ISS. We're looking for more opportunistic communications opportunities. We don't schedule our contacts. We could do orbital prediction, and we do, to determine when we would have communication, but it actually doesn't line up all that well with the actual abilities. And so the changes that we've requested basically go towards improving the utilization of the comlink without needing that contact graph plan. And I believe Scott would like to add on to that.
Yeah, I'd like to amplify that just a little bit and point out that, just as Tyler was saying, the protocols themselves are not modified at all for any of these adaptations for ISS. And in fact, the structure of the bundle protocol, the structure of the DTN architecture, is specifically designed to be able to accommodate the kinds of changes that we made here. That is, the changes were made strictly in the modules that manage storage, that do resource management in the implementation, and in the modules that operate at the convergence layer. The structure of the DTN architecture has been intended from the beginning to be able to accommodate a very wide variety of operational scenarios. And ISS is at one extreme of one of these, but that's why DTN is actually suitable for something like ISS. It's suitable for something like an interplanetary mission like talking to Mars, and it's suitable for data mule operations in terrestrial networking. The same structure works fine because it's all based on protocols that are unaffected by changes in venue and principles of non-conversational communication that lend themselves to all of these kind of wacky environments that are very different from what the internet was originally designed for.
Anybody else?
All right, well, I appreciate your time today. Thank you.